Okay, cool. It's the last talk. Everybody gets so excited for this guy. Oh! Okay. We're welcoming to the stage Felipe Argento. We're going over gas metering, comparing app chain rollups versus general purpose rollups.
So hello everyone, I'm Felipe, and it's an immense pleasure to be here, so thanks for everyone involved. At Cartesi, we've been talking about app chains for a very long time, and something that's quite surprising is that we don't hear a lot about gas metering. So I only have 5 minutes, but this is my attempt to kickstart the conversation and maybe give you some intuitions about it. So there are some reasons behind the gas metering system. The one that we're interested in this presentation is gas metering as a defense against resource exhaustion attacks. And what do I mean by that? So imagine that Ethereum is being attacked. There's a malicious transaction that is trying to halt the network, or either halt it or slow it down. What would you do? Well, you cannot know that the transaction is malicious beforehand because of the halting problem. Normal servers deal with this with the wall clock. So basically, you start executing a transaction. If it's taking a long time, you just bin it or you schedule it for later. Unluckily, the wall clock, unlike our legal system, is not deterministic. So we cannot use it because nodes would get confused about the validity of transactions. So that's a bummer. That's why we have the gas metering system, which is basically associating a gas cost to each OP code or each instruction that an EVM transaction executes. And this gas cost aims to correctly infer the cost of running that OP code on a real computer. Then we give each transaction a gas allowance and each block an upper gas limit. And we expect the reference node, to be able to execute a block of gas limit X on time Y. But what can go wrong? Because it sounds very simple. The problem is that these estimations are quite hard to do, especially when the architecture that you're emulating differs a lot from the architecture that you're emulating it on, which is the case with the EVM. Also, it doesn't help that mispriced OP codes are quite dangerous. And the average case for executing an OP code, it's quite different than the worst case for executing it. Also, a quick reminder, you have to use the worst case because otherwise there's a huge security problem on your chain. What went wrong? So in 2016, I was not around at the time, but during Shanghai Devcon, there was a massive DDoS attack on Ethereum. Part of the attack was malicious actors using the self-destruct OP code to trigger empty accounts. And that OP code was mispriced. What made it worse was that attackers were able to deploy custom code to specifically trigger the scenario in which the OP code was mispriced. And then we had to ask the miners to reduce the gas limit. That hurts scalability. And we had to hard fork and increase the gas cost of some OP codes. So let's talk a little bit about app chains. So the difference between app chains and shared rollups regarding the threat model is quite simple. On shared rollups, we have two possibilities of malicious agents. You have users that can send malicious data, and you have applications that can send malicious code. For application-specific rollups, the application and the chain are the same thing. So the only possibility of attack comes from the malicious users, which can only send malicious code. And this is a very important distinction. Just summarizing it real quick, on shared chains, you have adversarial metering. So the granularity is per OP code. So you're charging money per OP code, which is a very small granularity that has a big overhead, as you can see on the slides. The threat is data and code. So that means that it's quite hard to estimate the OP code cost, and also that the worst case is much worse than the average case. So you can see there, the worst case and the average case, there's a big difference there, and your block size has to be small. For Oh, also, the reference computer is quite idle even when the blocks are full in average, because you have to go with the worst case when your average case is much better. On Appchains, you can actually charge gas per interactions. So attack a goblin, gather some loot. And the interactions, they actually contain millions of instructions. So the overhead is much smaller. You don't have to calculate the gas cost every single OP code. The threat model is much easier to deal with because you can only have malicious data and not malicious code. So the worst case is much closer to the average case, which in turn means that we have a much better block size and therefore even more scalability. So that's it. Thank you so much. And yeah.
Okay, cool. There was only one question, which was, how did you become so damn handsome?
Oh.
I don't know if you're supposed to answer that.
I think I know who sent that.
Oh, okay, cool. What about using, oh, sorry, I got distracted. What about using average NR of computer cycles? Validators could post them periodically.
Yeah, so the cool thing about Appchains is that you can actually customize the best gas metering system for your specific chain. So we can even do stuff like cool stuff like subsidized transactions that help the ecosystem. You can charge differently if there's a lot of transactions coming of that type and etc. So that's a possibility for Appchains, yeah.
Okay, cool. I think that's everything.
Thank you so much.
Thank you.